Yeah, so when you look at this, you go like, wow, we do carry a lot of information ourselves that never make to protein. And you might think, oh, what a waste. But people are studying this, and actually a lot of the sequence that is regular, that is non-coding, is regulatory sequence, which just means it's a lot of red tape in the cell. It's a lot of like, when should we express this gene? So things are more tightly controlled. That's one of the reasons why there's so much non-coding. And then this bottom part here, it's like, okay, we have a bunch of non-coding in terms of how much overall, right? Total genomic is non-coding plus coding. And then we think we have the most coding because, you know, we are the most evolved. But actually, this guy here is rice. So rice has a lot of coding sequence. And a lot of it is because of something that you're going to hear about, I think, next class. They are transposons or retrotransposons. So there are retrotransposons, they enlarge a genome. And if a transposon has an enzyme called transposase encoded in it, then it's going to count as coding. So that's why rice has a lot of coding DNA, which is like kind of humbling to us, right? We have like half of coding as rice, but maybe you're more efficient. You know, we are planting rice, rice is not planting us. Anyway, that's just my spin of like, how interesting the world is. Okay, well, we already went over the answers to this one. So here's what I wanted to think about. If you think of human genome, for example, what is this? 3 million. Yeah, this is the size of the genome. Normally I see 3.2, not 3.1 giga base pairs. So yeah, just think there are 3.1, 3.2 billion base pairs. And then out of that, we have some things that are genes and other things that are intergenic. And then of the genes, we have parts that are exons. So exons are the DNA sequence that after they're transcribed, those sequences are translated. So that's what ends up in the protein sequence. And again, then when it says related sequences, you're like, what does that mean? So they are the parts of the gene that don't get translated. And then these pseudogenes, we think about them as fossils of genes, meaning they maybe get transcribed, they don't get translated, but mostly we think about them as they used to be genes, but there was some mutation and they are no longer transcribed. So we don't see gene expression of that DNA sequence, but it seems like it's a gene. Gene predictor software might say, oh, there's an ATG here, there is a stop codon here, there is a Tata box here, it looks like a gene, but nobody ever sees transcription, evidence of transcription. So those are pseudogenes, so like fake genes, right? They were genes, they lost some features, so now they're no longer transcribed. And then there's a bunch of intergenic DNA. These interspersed repeats, so these guys, I'm going to talk about these guys. They are repetitive sequences. And this we talked about, I called them SSRs, but they can also be called microsatellites. So this I am going to refer to when I talk about transposons and retrotransposons. But that's the overall genome sequence of humans, and then all of these is non-coding. So the only coding is this stuff here. It's pretty amazing. All right, do you guys have any questions?